The next Diamond talk is given by Peter Winzer. Peter is the founder and CTO of Nubis. Prior to Nubis, he worked at Bell Labs for 20 years, where he set multiple high-speed optical transmission records, contributed to optical communications product developments and live field trials, and led Bell Labs fiber optic transmissions research. He has published over 500 scientific papers, holds over 100 granted patents, and has been widely recognized with awards including the John Tyndall Award. He has named Bell Labs Fellow of the IEEE and Optica, and Fellow of the U.S. National Academy of Inventors. Peter is a member of the U.S. National Academy of Engineering and holds an honorary doctorate from the Technical University of Eindhoven. Peter.
Thank you very much, Hossein. Thank you very much. So welcome, everybody. I'm going to talk about CPX, which is a way to operationalize CPO for real-world AI clusters. So we've heard a lot about the bandwidth demands of AI, and my favorite chart to visualize that is this roofline model, which was talked about 2 talks ago in this session as well. So I'll just quickly review it. What you see here is the system performance in terms of flops per second that a compute system achieves, and it's plotted versus the operational intensity of the algorithm running on that system. Now, what does this operational intensity mean in flops per byte? It just tells you how data hungry is your algorithm. So very data hungry algorithms that perform very simple calculations on your data, fetch data into the processor, just perform simple calculations, have a low operational intensity. Not so hungry algorithms that perform very complex calculations on the data they get out of memory have a very high operational intensity. And if you're just limited by your processor, then it's a straight line here. You're not dependent on the operational intensity of the algorithm. Only if you have a very data hungry algorithm, you start to be I/O limited. That's when you see this slant here. That's called the roofline model, and that's very widely used in computer architecture design. And what you see here is several data points and rooflines of existing processes. That's a fairly old paper from 2017 from Google. That's a more recent paper by Cerebras using their architectures. So you see how these rooflines vary and where the various algorithms are. So they can be anywhere between 0.1 and a few thousand in reality. Now, particularly interesting is that orange roofline, which is the NVIDIA B200 roofline. So you see here the I/O limited performance due to on-package memory, and here you have the processor performance by itself. And the dotted line is the scale-up domain I/O limited performance. So it doesn't matter where you are in terms of operational intensity. One thing is for sure, every AI system could use several orders of magnitude more I/O bandwidth. That's really what that chart tells you. So how do we get to that I/O bandwidth? The currency of the data center over the last quarter of a century has been the high-speed SerDes. So high-speed SerDes have served us well and are still serving us well. You see here the evolution since 2000 of the switch capacity of Ethernet switch chips, as well as the per lane switch I/O, scaling only at 20% per year, while the switch capacity is scaling at 40% per year, which just means the curves are separating. In other words, the chips have more I/O lanes. That's what this really means. And we're talking about 512, 1024 I/O lanes today. And that's here, Tomahawk 6, 100 terabit switch, and then you see projections of when we might have 200 and 400 terabit switches. And we are at 200 gig per lane today, and here is when we might have 400 gig per lane. But these are picture-perfect exponential scaling curves, and there is no sign of slowing down. So 200 gig is here today, 400 gig will be here in due course. Now, one important thing is, why do you use SerDes? Why are they so important? Because they support copper. So there is this universal saying, use copper when you can and optics when you must. And this paradigm is true. This paradigm is supportive of SerDes or in other words, SerDes really support this paradigm. And that extends also to optics. So in order to build an optics interface for AI, you have to interface with high-speed SerDes as long as copper is alive, and copper is alive and doing very, very well. So today, you really have two choices when you do your AI architectures. You either use passive copper, which doesn't consume any additional power on top of the SerDes, but it only reaches 1 meter. Or you use retimed optics, which can get you to hundreds of meters and kilometers, but it uses quite a lot of power, 30 watts for a 1.6T pluggable. So that paradigm, of course, shows you why it's true. Use copper when you can and optics when you must. It's because of power, and obviously cost is related to that as well. And if you build architectures like that, the retimer DSP alone, that's part of these retimed optics modules, costs you billions of dollars in large cluster operations just because of your electricity bill, nothing else, just counting your electricity bill. Now, over the last few years, there have been two new kids on the block, and one of them is called linear optics. And linear optics is essentially a retimed optics module that does away with the retimer DSP. So it only has the optical engine and the laser inside, but no more retimer DSP. Advanced SerDes can drive those linear optics modules directly without a retimer DSP, and they slash the power down to 10 watts and can reach the same hundreds of meters to kilometers that retimed optics can reach. And there's also active copper, which are analog electrical amplifiers that boost the reach of passive copper from 1 meter to 4 meters at a very, very low power of 2.5 watts per 1.6 terabit. So the takeaways here are that use copper when you can, optics when you must is super well and alive and will continue. And the other thing is avoid retimer DSPs at all costs, because that allows you to save billions in your electric bill. And to quantify that a little bit, there is an example study here for a 150K XPU scale-up cluster or scale-up domain, achieving 25.6 terabit per GPU with any-to-any connectivity. And you, like an architecture like this, like a two-tier scale-up domain, where you use a mixed media. So you use passive copper here in this domain, call it a rack within a rack, passive copper, and then you connect to retimed optics for the tier 2. Or you can also do passive copper in the first tier and then go to linear optics in the second tier. And if you do that, you see what you gain. You have about the total power of your interconnect, including switches and all the links, because interconnect is switches and links, goes from 240 megawatts down to 150 megawatts in this example, or from 48% of your entire cluster power consumption to 37%. You might say that's only, that's really not a lot, that's only 11%, but those 11% are $320 million in electricity bill savings over the course of 5 years. So that's a lot of money. And it gets worse for larger clusters. So this is a 600,000 GPU cluster with the same all-to-all connectivity. So you go down from 1.7 gigawatts for your switches and links to 600 megawatts. You save $3.8 billion over 5 years. So those are very, very sizable numbers that you save there. And another thing that's very interesting is that when you go from passive copper to active copper in your first tier of your scale up, then what you do is you increase the scale up domain dramatically, because now you can reach like 4 or 6 racks instead of only 1 rack with passive copper, and you stay at the same fractional expense for your interconnection cost, although you increase the number of your GPUs dramatically by a factor of 4 from 150K to 600K. So how do you achieve that? How can you build these systems to allow linear pluggable optics or linear co-packaged optics? you need an enormous densification because pluggable optics today, OSFP at 1.6T, achieves about 0.14 terabits per millimeter in terms of its beachfront I/O density, whereas the 200G SerDes on the switch or on the GPU have 1.5 terabit per millimeter. So in order to avoid that, these long electrical traces that go from the SerDes, from the SerDes that's embedded in the switch all the way to the front panel pluggable, you really need to move those closer to the chip. Why do you do that? You do that to make linear work even for higher rates like 200 gigabit in a reliable manner, because you can't have those long traces. That doesn't work. And then if you plug those into copper cables, that also doesn't work. You need shorter cables. You need a densification of the system, which you get by putting more GPUs, more switches in one switch tray. That's a densification that then allows you to have more ASICs in the same rack or in the same cluster of 4 racks, and use shorter cables to avoid retimers. So avoiding retimers is really the name of the game here. Now, one important thing, if you look at these architectures, you see those massive fan-outs because the number of GPUs is really given by the fan-out you have, or in other words, by the switch radix. So in order to get large numbers of XPUs, you need large switch radix. And in order to get you to a high bandwidth per GPU, you need a large number of switches. So AI networking does not really like big fat point-to-point pipes. It rather wants full fan-out networking at the SerDes rates. So when we talk about optics, there's always the question WDM or not WDM. WDM is the enemy of fan-out. That's something we need to keep in mind. And the reason is that full fan-out is very easy to do if you have single wavelength optics. You just have a fiber shuffle where you interconnect switches with GPUs. It's just fiber connections, a patch panel. It's simple, very low loss. If you build WDM interfaces, you first need to demultiplex your wavelengths. Then you can do your fiber shuffle, and then you need to remultiplex your wavelengths. So you have 2 extra elements, which adds complexity. It adds substantial optical loss, and it's expensive. So if you can avoid WDM, you will, especially for AI scale up. So now, how do we get to these high density? The high density you achieve by going from 1D to 2D interfacing. And that's true both electrically and optically. In the electrical domain, this is inside one of these pluggable optics modules. You have this edge card with the gold fingers. That's a one-dimensional interface that you plug into your system. And if you do a 2D interface, you have a much higher density because now you interface through the area and not through just the edge. It's a mathematically better scaling object. So you achieve 5 to 10 times better density. Optically, it's the exact same story. Instead of coupling fibers to the PIC using edge coupling just on the edge of the PIC, which is traditionally done, you go to 2D array interfacing by coupling fiber arrays to the surface of the PIC, which gives you a 5 to 10 times better density as well. So going from 1D to 2D interfacing is the name of the game for dense interfaces, both electrically and optically. Here is just a view how we do this in our PIC. So that's a cross section of the PIC that has the modulators, has photodetectors, and here you see this 2D fiber interfacing that goes onto our PIC. Now, it's very clear now what AI really wants from optics. AI wants low power, so support for retimer-free linear optics. AI wants high density, which means you need to be matched to the SerDes I/O that the chip provides. AI wants full fan-out, which means single wavelength per fiber. And AI also wants simple operations. It wants serviceability, and it wants a multi-vendor ecosystem like the super successful pluggable ecosystem that has fueled data centers for the last 20, 25 years. So here is how we do this for CPO. So co-packaged copper is already embedded in advanced systems where you have sockets of co-packaged copper that attach to the substrate of your ASIC, and then you plug twin X cables into them. And if you now design optics to fit into those exact sockets, which is exactly what we are doing, so this is a 6.4T removable optical co-packaged module, CPX module that mates into this co-packaged copper connector. You can think of this as a scale-up switch that speaks copper to the GPUs and optics to the next tier, for example. That's one application space. So very low power, 5 picojoules per bit or 5 watts per terabit. It's a retimer-free linear interface. It's matched to the SerDes I/O. It offers a multi-vendor ecosystem, fully compatible with copper. So that's a way to really operationalize those advanced AI clusters with enormous bandwidth demands and enormous scale out and scale up, because you need to have the large number of GPUs. This is the way to enable them. So the key takeaways here is you have to have mixed media support. So you need to interface your optics to high-speed SerDes for the next 5 to 10 years for sure. You need to enable full fan-out because that's what AI cluster architectures want, and that means single wavelength DR interfaces. You need to support the linear optics paradigm, which means get rid of your retimers, co-package your optics to make your electrical traces as low loss as possible, because that's what gets you rid of the retimer DSPs. And you want this in an operationally amenable context, in a multi-vendor friendly ecosystem, mixed media ecosystem, where and that's the CPX paradigm, where you replicate the successful front panel paradigm and transport it to co-packaged optics using the CPX. Thank you very much.
Thank you very much, Peter. There are some questions in the Slack channel, but because the panel is going to start right away, I'll let Peter respond to them directly on a Slack channel. Thanks again for all of you.
Thank you.